If you prefer. For the lab, it's very
Thank you.
important. For the course, it's not so important. So again, the title of the course, Finite Elements Analysis. This course, as I told you, was written by Professor Mircea Radesh. And this year, I will present it. So my name is Stefan Sorohan. And the outline of the content of this presentation is a short introduction, the object of finite element analysis, finite element displacement method, 6 basic steps for finite element analysis, sources of approximation in finite element analysis, and a short historical view in a few supplementary pictures. So, if you want to build, let's say, a finite element code, you must know or you must have knowledge from 3 different fields. The first one is structural mechanics. That means strength of materials. If I don't know exactly if you have more course of theory of elasticity. There is more or is no, you know, something about that theory of elasticity. I don't know exactly if you have more discourse. So dynamics, plasticity, etc. Also some knowledge about numerical analysis. That means approximation method, solution of linear set of equation, eigenvalue problem, and so on. And of course, applied computer science, which means development and maintenance of a large computer code. For the lab, we will use some small computer codes, but for example, ANSYS is a commercial code, and it is a very large computer code, and we have not access to the script file or only the exe file we can obtain. So the main idea of finite element analysis is this one. We can take a look at this picture. So let's suppose that we have a body, this one, a body with a general shape. It may be also a 3D. In this picture, we have just a 2D sketch. And this body is subject to some loads. Here we have a pressure or traction load. Here over this surface we have a fixed support. And this, let's say, elastic body, it may be from steel, for example, is under the study, and we want to see how is the format configuration, because as you know from strength of materials, a body is not rigid. It is deformable, and we can have elastic displacement for small loads, and if the loads increase and increase, the displacement may be also plastic or elastoplastic, and finally the body can be destroyed, or we can have cracks or something like that. But generally, for this course, we will study just elastic body. So the loads will be not so large to have a permanent deformation. And let's say we are interested in the maximum displacement and also maximum equivalent stress. For example, according to the last theory of resistance or von Mises stress. Yeah, maybe largest, let's say in this point here, we don't know exactly. Of course, for simple structure as beams, you have some analytical formulas and you can obtain the stress distribution and also the displacement. But for a general shape of a body as this one, we cannot use strength of materials to obtain the solution. And the finite element method is an alternative to obtain some approximation solution, not exact, but this kind of approximation may be very close to the exact solution if you want. How works this method? So please keep in mind that finite element method is not a discipline. It is just a method, and we can use it also in structural analysis. We can use it also in thermal analysis. We can use it also in electromagnetic fields and so on. And generally, we can say, okay, what's finite element method? And we can say finite element method is a general method which can be used to solve some differential equation. Usually, from mathematical point of view, all phenomena in engineering are described by such a differential equation with, of course, with partial derivative, if you want. So the idea is, okay, we cannot obtain a solution for all these fields, for all this body, but we can split this body in small parts, let's say these triangles here. And we assume that these triangles are connect each other only in some particular points, let's say these points here, or in these points here, we have connected many triangles. We call these triangles as finite elements, and we call these connected points nodes. And of course, if we discuss the displacement and we take a global system of coordinates, let's say x and y, we can define 2 degrees of freedom per node. That means displacement along x and displacement along y. You will see later in the next courses that these degrees of freedom are according to a global system of coordinates. And we can define in each node, as I told you, 2 degrees of freedom, let's say capital Q, and we have also some numbers here, some identification number. For the moment, is not very important. Of course, for this method, we must use a computer, because without a computer, we just can point out some important steps in finite element stage, but a real problem is solved with the finite element code. And when we use a computer, we need to collect all this data in some arrows, and we must have some identification numbers for nodes and also for elements, and we will define some vectors later. This is the reason why for the lab we will use MATLAB or Octave, because MATLAB works with vectors and matrices. So the idea is, instead of analyzing the initial body, we can make some analysis for this system in which we replace the initial body with some simple body, which in this example are triangles. Don't forget the triangles are connected each other only in some particular points, and these particular points are called nodes. And then, as you can see, we have a loft-dot triangle. We can take one, an arbitrary one, as this one here, and also using a system of coordinates, which is not plotted here, we can define in each node. So this triangle have 3 nodes, 1, 2, 3. And we can define in each node 2 degrees of freedom. Again, so displacement along x, along y. As you can see, for this displacement, we have some identification numbers. So this is u1, v1, u2, v2, u3, v3. Yeah, inside of this element, which is generic denoted with small e. So an arbitrary element from this one is denoted e. And we may suppose that inside of this triangle, displacement u and v, which is a continuous one. So we have an infinite number of points inside of this triangle. May be written function of nodal degrees of freedom. This is the key point in finite element analysis. So we have an approximation. We approximate that this displacement inside of this triangle are function of nodal displacement. But this will be discussed later, just to have an idea. So again, the main idea, I have a general body. Its shape is very complex. We split the body in more simple shapes as triangles or sometimes quadrilaterals in 2D. And we consider that these smaller bodies or finite elements are connected in some nodes. We introduce some degrees of freedom as displacement only in these nodes. We make some theoretical assumption here, and we can obtain some relationships for each element, and then we can consider the assembling of this or interaction of these elements, and we can solve a complex problem. And this kind of split the initial field in smaller elements is called discretization. Sometimes we call this operation mesh in finite element codes. Instead of discretization, we will use mesh. So generally, according with which I told before, we have 6 basic steps for finite element analysis. The first one is to take the body and to make a mesh, or to discretize the continuum. Then inside of this element, a particular element, we must select some interpolation function. You will see that these interpolation functions are usually polynomial functions. So we need to know the continuous displacement inside of this element function of nodal displacement, and this one means I must select. I will make a choice. This is the reason why the finite element method is not an exact method. It is an approximated method because we make a choice, and this is the arbitrary. Then we must find the element properties. What means that? So this element have an area. We must know the nodal coordinates for node 1, 2, 3 for each element. This element may have a thickness. This element may be from steel, and the steel have some properties as Young modulus, Poisson ratio, mass density, and another one is not all the constant, but maybe property. Then we must assemble the element properties. So for each element here, we can use the theory to write something. Then this kind of information is just for an element, but we need the information for all body. That means we must integrate, or we must assemble the element properties. After that, usually after assembling process, as you can see, we have many degrees of freedom. This one here, this two here, two here. And as you can see here, we have some identification numbers for nodes. Node 1, node 2, 3, 4, 5, and so on. The last one may be 16 here. That means 16 times 2, 32 degrees of freedom. For these 32 degrees of freedom, after the assembling process, I will obtain 32 equation, or if you want, a system of equation with 32 unknowns. So usually we cannot solve this system of equation without a computer. We need a computer and also a soft for that. So usually this kind of system of equation is a linear one. So after solving this kind of equation, we will obtain all displacements here. After that, if we go back to each element, and if we know the nodal displacement, we must obtain some derivative quantities as strain, stresses, sometimes reactions here in this fixed part, and so on. So please keep in mind that according to the book of Professor Radesh, we have 6 basic steps for FEA. Okay, we have a lot of approximation, but 3 main sources of approximation will be given in this slide. So the definition of the domain. So physically of geometric and geometrically. So physically means that we must know some material properties, Young modulus, Poisson ratio, and so on. Geometrically, we have a shape. Let's go back. And please observe the shape of this body is not filled completely with triangle, because here we lose part of material due to the reason that this element, this triangle, have straight line. It have not curved line. So this is an approximation for the geometry. This kind of approximation is mainly due to the discretization here, and which I told you is called here cutting the corners, or making curved lines straight and curved elements flat, and so on. But also, if you want the geometry, sometimes when you use a CAD program, you can neglect some, let's say, small radius, small holes, and so on. And usually we don't make an analysis for the real geometry. This is due to the discretization, if you want. And also we can have the approximation for the solution algorithms. In these solution steps, we must make a lot of modeling. We must modeling some joints, contacts between some parts, damping, for example, in dynamics problems. But generally, please keep in mind that the boundary condition boundary condition usually means supports and loads. Supports means that somewhere we have some displacements which may be known or maybe also zero. and the forces are the loads, the pressure maybe also the force. So boundary condition in the when we must use this kind of problem are very important. Why finite element is so general and was universal accepted? You will see the routine choice of shape function is very simple to be used because we use polynomial functions. It's very simple to producing so-called stiffness matrices. What means a stiffness matrix? You will see later. I can explain for a single degree of freedom. Let's imagine that we have a spring. The equilibrium for a spring when we have a force is K times X. X means displacement. So K is the stiffness. We have something like a spring also here, but instead of a single constant, you will see that we obtain a stiffness matrix. Yeah. And it is a versatility. If you have code, you can change the input data to develop a different problem without difficulties. Finite element modeling process, according to Professor Radesh. Okay, let's go back here. As you can see here, I told you that the displacement inside of this triangle will be a polynomial, but we can take first degree polynomial, a second degree, and so on. The polynomial is not unique. And that means because we make a choosing, we must choose the correct and appropriate type of elements. We have not only triangles, so you will see later we may have also in 2D quadrilaterals. And choosing of the interpolation function is important, and for each interpolation function we can define a different finite element type. Okay, if you use the finite element codes, you will see that there we have a lot of finite element types, and we don't know all about these element types, but you must understand that it's very important to read something and to understand minimum information if you want to use the elements. So it is something as a pedigree, not spotting wrong answers due to the use of inadequate elements. So you will see sometimes the results are not good because the method is an approximative one, and if you make bad decision when you take a finite element type, then when you use a mesh, the answer is not good. So you must keep in mind that and see where the results is not good and why, on some spot points. The assembling of the elements is or will be presented in the course 3 and 4, so later. But keep in mind that the code make this one without problem because it's an automatic process. Solution also is done by the computer. So, but the input data is our responsibility. And after the solution, again, we must use the displacement for each element to define other mechanical quantity as mainly stresses for begin. This is a connecting rod with a mesh using so-called hexahedral elements. So as you can see here, this body is divided, is meshed with some particular finite elements, and these particular finite elements are hexahedral elements. Oh, this is a car engine piston. As you can see, again, we have a mesh with hexahedral elements. This is a vehicle out of frame, if you want, cabin. And we have also some springs here and some quadrilateral shell elements. Shell means finite elements with 6 degrees of freedom per node, free translation and free rotation. You will see at the end of the course something like that. A cooling tower, and this is a dynamic response, if you want. Vibration, you will discuss this one in the second semester with Professor Angel. Viorel Angel will present you the dynamics of and vibration in the second semester. Sometimes this is a crankshaft, and this picture means something as an animation. Yeah. And as you can see, the discretization or the mesh is also with some hexahedral elements. Sometimes the mesh may be improved. So this is an initial mesh, and if we apply a force in the contact of this gear teeth, we can increase the mesh size, the number of elements. So the size of the elements will be smaller. In this region where we will put a force or a pressure from contact, and also we will increase the mesh somewhere here and here where the stresses are large due to the bending of these two. As another example in 2D, this is a plate with a hole. Due to the double symmetry, we take just a quarter. We make a mesh, something like that. We put some pressure or boundary condition as loads. Also, we impose some boundary condition as displacement. So these points here move only along X, and they are fixed along Y. These points here can move only along Y, and they are fixed along X. And we can obtain, let's say, the stress distribution as in this picture with different colors. This presentation is on old one, and we have just instead of color, we have different kind of hatch. Again, the same problem with a different mesh. This is the load, some dimensions, and this is the book. So please keep in mind, this is important for you, that the final mark will be obtained from the lab, 50 points. So that means each lab means 5 points, and the last 4 labs will be more difficult because in the last 4 we must use the MATLAB code and also the ANSYS code for to solve the same problem, and only some students want to use ANSYS or learn something about ANSYS. So the first labs will give you maximum 50 points. The remaining points will be at exam, but the exam means 10 points the course presents, 20 points the homework. You must solve a homework for the exam, and only 20 points will be exactly at the exam. The 10 points for a computer problem, you must solve a real problem, for you will obtain a subject, and 10 points means the theory. As you will see, the theory is not so simple, and the theory will be oral, just one or maximum two questions, and you must give answer for that. So this is an old presentation. Usually I have not time to make good presentation. I will use for the course, I will use directly the book and I will explain a lot. Later I will make some draws for you. Of course, there are a lot of books which may be used. As you can see here, Romanian version of this is also written by Professor Radesh. You will obtain these two books. And I have a book also for my students at which some of students from Faculty of Transportation in where is it? No, this is fair. Huh? So this is another book, but is it just in the draft version? Yeah, and the English here is not so good, because as you can see, I'm not a good English speaker, but yeah, let's take a look here. So my course, something is different. So this is the domain, this is the mesh or discretization. If you want, I can give you also this course, something general aspects also in theory, different types of finite elements. Yeah, this is important. You can make a zoom. So we may, if you want, we have some classification of finite elements types. So we have 0-dimensional, unidimensional, bidimensional, axisymmetric or 2.5D, and 3D elements. And 0 means a concentrated mass, a particular spring. Unidimensional means a bar or a beam. Bidimensional means a triangle or a quadrilateral. Axisymmetric means particular elements which can be used for axisymmetric structure, like a glass, for example, or a bulb, or three-dimensional may be tetrahedral elements, hexahedral elements, also some wedge or pyramids, but not so used. And as you can see that we have triangles with more nodes, with 6 nodes, and this kind of triangle may approximate better a geometry, because it may have a curved line here instead of straight line, because we have more node in the mid side edge here. And also for this one and for three-dimensional elements, it's also possible. You can define elements with more than two nodes. You can have two inside nodes here over the edge. Yeah. But in time, you will see all of these aspects. I can show you in let's say 10 minutes, and after that we will take a break. So I told you that it is possible to use also commercial finite element code. There is a code which is called ANSYS. This code has a free license for students. Yeah, this is academic teaching introductory. You can download this program if you want from ANSYS site, ansys.com. And here you have academic free trials I support, or free software student download now. And if you want to use ANSYS, or if you want to understand or start to work with ANSYS, you can download this ANSYS student version. Yeah. Better is to have more than 4 gigabytes for RAM memory. Yeah, if you have 8 or 16, it's better, or even more. So this ANSYS may be used to solve a lot of problems. Let's say I will define here for this one. So let's say in this directory, I will define a new directory demo, and I will put this model exactly here in this work directory. And this is, let's say, demo 1. So this is a finite element code, a commercial one. It's not very simple to use, but I will show you just in a few clicks, because it's easier to see on white. I will change the background here. So as you can see, this finite element program can be used for structural, thermal, electromagnetic fields. Yeah, I will take structural, and here you can see that we have a lot of finite elements. So quad, bricks, so as you can, tetrahedral, axisymmetric elements. There are a lot, more than 300 of different element types was implemented in ANSYS. So let's take, for example, this one. You can take a material or put some constants for a material, let's say Young modulus here. Please remember the Young modulus in megapascal means 2E5. This is Poisson ratio. And you can model something. Let's create an area, rectangle area. Let's suppose that we have an area with 100 millimeter over X, and let's say only 10 millimeter over Y. Please observe here a system of coordinates. This is called the global system of coordinates. Then we can define a mesh. Let's use triangular elements here, and let's mesh this area. So as you can see, we have this field and some shapes, which are triangles. Of course, these points are have some numbers, identification numbers. So this is node 1 here, node 2 here, node 16 here, and so on. Also, the elements have some numbers. This is element 7, 19. So the number, the identification numbers is random if you want. 1, 2, 8, 7. Yeah, we don't know exactly. We have not a rule here. I will remove the element numbers and we can use solution to apply boundary condition. Let's suppose that this line here is fixed. Sorry, again. All degrees of freedom, ux and uy, means displacement along x, displacement along y. 0 here means 0 displacement or fixed. And I will take a force. I will put a force here. The force may be along x or y. Let's say minus 100 Newton. If you plot the area, you can see this is the field, this is the geometry. For this one, we have also an analytical solution because it is very simple, but for general problem, this one is not so simple. And we can save and you can solve this problem. So we have some warnings. You can read if you want the warnings here in the. So mesh is not so good. This is the message. I will neglect it. So solution was obtained. I will read the results in the program. And we can plot, let's say, the deformed configuration. So due to the force here, this body have a maximum displacement here around of 1.32 millimeter. This displacement is not a real at real scale. If you want, this is from steel. If we change for true scale, we observe that the displacement is small. It's not so large. Also, we can plot, let's say, the stresses along x, and we find here positive normal stresses 267, negative stresses here due to the bending. Please observe that we have bending here. So this is the region where the stresses are larger, as you know from strength of materials, and also we can obtain the equivalent von Mises stress, for example, which show us that also the maximum stresses are in this region. Of course, this is just a demo. For you, this kind of problems you will be able to solve starting with labs 7, 8, yeah, till the lab 7. We will discuss just beam or bar elements, and today something similar with this aspect, but I will show you after the break. And also after the break we will make a short history of finite element development. So 10 minutes break.
Okay.
So I forgot to tell you, if you have questions when I present something, please ask me, because it's very important to understand the aspects in real time. So not too many students in the same time, but if you ask, there is not a problem. Okay. In 10 minutes, I will be back. Okay, I'm here. May we continue?
Yes.
Yes.
Okay. I prefer to present in this second hour of course something about the lab, because the lab is very important for your activity and also in practice. The theory, of course, is important. We will discuss more in the next courses, but for the moment we must prepare the necessaries for the lab. So, as I told you, we need Octave. We need Octave because we have a lot of finite element codes. I will give you all together or one by one. For example, for the first two labs, we use just these files in this directory. In means mominert, or if you want, second moment of area for cross sections. And after that, we will use also frame, truss. Where is truss? Is not here. Finite element truss, and constant strain triangle, linear strain triangle, and so on. And if you want all these codes, I can give you, but usually I will check that in this new version of Octave they works. So better is to take only the code which was already verified by me, because for beginners is not so easy. So to download this one, you must find, let's try to use free download Octave. Yeah, and after that, I suppose that you use Windows on 64 bits, so you take this one, which is recommended, and not necessary now. And you will obtain Octave here in this on desktop, for example, and you can run it. So Octave or MATLAB is the same. The difference is that Octave is free. As you can see in Octave, we have a main or command window here where we can define some parameters. Let's say A1, B is 2, and we can obtain C is equal A plus B. And we obtain the answer. We can define also, let's say, vectors or matrix. Let's say a vector is defined as something like that. This is 1, 2, 3. This is a row vector. We can define also a column vector as, let's say, 2, 3, and 4. And if you use transpose here, yeah, you will obtain a column vector. We can make vector multiplication, let's say A times B, and we will obtain a number, because the number of line is 1, the number of column is 3. Here the number of line is 3, the number of column is 1. So if you define, let's say, matrix, let's say 1, 2, semicolon, 4, 5, you can obtain, let's say, the determinant of this matrix. I'm not sure that you know something about MATLAB. If you know, please tell me, because I will omit to present these very simple aspects. Of course, we have not time to present more, but I have some documentation which will be loaded on the Moodle platform. You can read it and you must understand better. So also in MATLAB or Octave, you can build some functions. Here we have so-called M function. M function, yeah, may be a script file or even a function. The difference will be seen in the time. So for today, we will use some codes which I suppose that this is for course for lab. Some codes which are here in this directory, momin 3, 4, 6, 8, and 9. Just to see one, and after that we will start some particular application. So usually you must go inside of this directory. For example, this is momin 3, and you can see there is a name which is the same with the name of this last directory, and this is the main file which run a particular problem. Usually in Octave we must work in the same directory, so I will copy this directory and I will change the current directory here. You can also use cd, change directory, Ctrl V, and as you can see now, the directory in which I will work will be this one. Here you can see all the file from this directory, and of course this is the main file which may be open. Let's open it. So as you can see, this is a code with some comments here, yeah, which was written by Professor Radesh in 2008 if you want. Yeah, it works in Octave. This was my comments in was a little bit corrected, and a lot of command line clear all. That means the program will delete all the variables in working space here. So we have this one. If you will use the command Windows, and if you will use no more variable here. So again, and clear screen and so on, input dot mom3. If you will see here, we must have a name, yeah, this one. Let's open it. So more file here. In this file is filled with another commands in MATLAB for analysis, and this is a program. For us, it's not necessary to understand all of that, because we are only users of this code. But if you are interested in that, you can read it and you can understand more. So in command line, if I will put the name of this code, let's say mom in free, the program will ask for an input data file name. The input data file main usually are, we have some examples here. So for example, I have x min 1, x min 3. Let's take one. I will type x min, oh sorry, x min 9, for example. The program reads this input data file and give us some general information. As NN, we will see later, means total number of nodes. NE means total number of elements. NNE means number of nodes per element. So we have triangles here. Nodal coordinates means for each node I have x and y coordinates. Let's suppose that here the units, it's our business. Then we have some element data. So for each element 1, 2, 3 till 6, I have node 1, node 2, node 3, and some numbers here. And that's all. After that, the program starts to make some calculation, give us a picture, figure 1. Then if you will use enter, you will obtain some general information. The cross-section area for this figure, it's here. The second moment of area about initial arbitrary axis are given here. No units, because the program doesn't know the units which was used. The cross product of moment of area is given here. The static or the first moments of area are 0 due to the symmetry, and the centroid coordinates xc and yc. Again, the product moment of area about centroidal axis, and the second moment of area about centroidal axis are given here. More on enter, we obtain a new picture, and these are the principal moments of area. I1 and I2, they are all times positive. Please remember from strength of materials. I will go back later. And more on enter give you also the principal direction 1 and 2 according to these numbers here. And that's all. And the program. So don't here you will have the picture. You can close them, or you can keep it if you want. Sorry. And as you can see, the program, but what means these numbers here? You must know some theory, and you must how the input data file is. Let's open this xmin9. xmin9 is an input data file, is a problem from a book. RM means strength of materials, rezistența materialului 1, yeah, and this is an example for a book of Professor Radesh, and we have some data as date gen is a row vector, date node is a matrix because we have more lines for each node, and we have a more matrix date lm, which is also a matrix. For each row we have node 1, 2, and 3. Okay, we may obtain the information from a file. I suppose that readme, we have a readme. Let's open. From this readme you will see how the angle is defined. So 1, 2, 3. Yeah, please keep in mind that we have this information. Also, you can see here input data format. And again, this one is the code, which will be read, not important. But usually when we solve a particular problem, the easier is to take an example and modify it to particular inputs. So first of all, for this lab, I will show you. Please remember, this is the first picture from a string of materials. If you have a rectangle in a rectangular cross section with base B and H, the second moment of area according to this centroidal or principal axis are BH at power 3 divided by 12. I suppose that, and this is the area. Yeah? I suppose that there is not a problem for a circle. We have this formula pi diameter at power 4 divided by 64. For a general triangle, we have this one. And as you know from string of materials, it's not very simple to obtain the second moment of area for a complex cross section. For example, let's close also this one. Our application for lab number 1 and 2, because the first lab is not so simple and you have to work a lot. We will use 2 labs to solve this problem. You will see that here we have different cross sections. For example, the first problem, M1, means a circular cross section with 4 holes. The second one is part of circular cross section with a circular hole, and so on. We have a lot of 28 problems here. We have also for each problem what we need to obtain. So here is written, determine the second moment of area above the centroidal axis. Of course, due to the symmetry, we know the centroidal axis here. And compare the results obtained using meshing with 3 linear triangles, 6 node quadratic triangles, and 4 bilinear, and so on, finite elements. As you can see here, these problems are for you. You have a number from the list of the group. I will give you that later, and you must solve your particular problem. So the first student in the group will take M1. The student with number 16 will take the problem M16, and so on. But a little bit later. The lab must be solved, and the results will be filled in this table. As you can see, for this problem, moment 3, we must use this kind of triangle. For moment 4, we have quadrilaterals. For moment 6, we have triangles with curved lines, with more nodes. These numbers here means the node numbers. So this element is defined as node 1, node 2, node 3, node 4, node 5, node 6. In different codes, this node numbering may be different. For example, for moment 8, you must have 1, 2, 3, 4, 5, 6, 7, 8. The node numbering of one element for this one is 1, 2, 3. It's different, 4, 5, 6. Yeah, you must keep the rule in the codes. This is important. And I will solve a problem, let's say, for the first code, and also for this one or another one. I will take 2, because the remaining one are similar, just we change the shapes of discretization. You will obtain also this file to fill directly in it, and here conclusion in, and if you want you can put also the input data file, the results, but what I will check are these numbers here. Please keep in mind that sometimes, because this is your numbers, I have here only 23 students till now. If you are more than 23, I will add here, but this is the last list from this morning. Will be also put on the Moodle platform. For MATLAB, I will put there some tutorials. For example, if you take one, you can use some simple commands to understand better the Octave if you don't know, or this one, yeah, with more, this is in French, yeah. They were collected by Professor Radesh. Yeah. Will be for you. This is exactly for MATLAB, but Octave is very similar. Yeah. And the codes are here. A little bit about theory. We suppose that you know the theory, but let's remember. I will use a personal file. This is in Romanian, but is not important for you. So let's suppose that we must to obtain the second moment of area or geometrical property of this general cross section, like that. We will take a global system of coordinates x, o, y, and according to the theory, yeah, the total area or the surface of this, the area of this cross section is the integral from this elementary dA. So this is the sum of this area. The static or the first moment of inertia, according to this picture, S according to x-axis is y coordinate. That means y is this one here, multiplied with the a and integral over the complete surface. And this similar is for y-axis. The centroid of this cross-section area may be obtained using these general formulas. So we need the first moment of inertia, and the second moment of inertia first are obtained according to initial axis, according to a similar relationship. Please observe that here is y square. This is also positive, the a. So this ix is all times greater than 0. It's positive. Similarly, the second moment of area according to y-axis, it's positive because this x is square here. The cross moment of inertia is the product x times y dA. This one may be positive, negative, or 0. Please remember, when we have a symmetric structure, a symmetric cross section, this one is 0 due to the, you know that from strength of material. And using the Steiner relationship or the parallel theorem axis, we can obtain the principal moment the centroidal moment of inertia. And after that, please remember, if the cross section is general, we have two axes. For each, the cross product moment of inertia is 0. So I12 will be 0, and this principal axis, or for this principal axis, the moments of inertia are obtained using this relationship, and this is the angle which define the direction, and another angle if you want to for the second direction. So remember that I1 plus I2 it's equal with IXG plus IYG. Is not written explicitly here, just this one is written here, but you know that from strength of materials. The first one is maximum, the second one is minimum. Of course, this is a different similar finite element code. This is my finite element code, which I used it for another students. And we can have here just quadrilaterals with curved lines or straight line or even triangle line. It's similar. The theory which is used here, as you can see, it's complex. You cannot yet understand the basics here, because as you can see, we have some interpolation functions or shape functions, and we have some Jacobians or something like that. So it's complex. Please neglect this aspect, which is no important. For today, for the labs, is important to understand the results. And as an example, I will take a particular problem, and I will try to solve in Mominer or Momin. Yeah. So our is fair. This is the, of course, I will change because, so the subjects will be given, the file will be given on the platform. And now I prefer to take an example, particular example, and I will start with this problem. Let's make a sketch for a new cross section. And for that, let's use Paint, because I have not yet a tablet, but I will try to obtain one. So let's suppose that we want to find the second moment of area, the centroid for simple cross section. We can take a circle, or better, I will consider only a quarter. So I will remove this part here. And let's suppose that our cross section is this, and let's suppose that the radius is let's say 10 millimeters. So we are interested to find the centroid, and also the most important is A1 and A2, the last numbers in the column. And also, let's say, the cross-section area is also important, E X, G or C, and so on. So the input is just this radius. I suppose that is no more necessary to put exactly. If you want, you can put here, this is the radius here. No, so sorry. So this is the radius. How can we solve this problem? As you can know, we must make a mesh. For that, I will take a quarter of this one. A good idea is to use, let's say, the math paper or something like that to keep the scale. But I will take small thickness for lines. So let's say that I will make a large circle, and after that, it's not perfect, but I will oh, the idea is, okay, if I want to obtain and use the code, I must make a mesh. How? It's arbitrary. The simplest one is to split this one, let's say, in only in two triangles. And for that, I will put, let's say, some nodes. And so I need a node, oh, here in this point. Another one I need to be here. Another one I need to be here. And let's say for a first mesh to put just one here at an angle which is 45 degrees here. And then I will put more lines, and let's say this is the first triangle, and this is the second triangle. Of course, I will neglect this area here, because in reality, using this kind of mesh, I will have only these two elements. Neglecting this part is not so good, but later, if you want, you can put more nodes here and here, and you can improve the mesh. More nodes means a mesh which is better, and the mesh better represent this initial area. But let's keep this one. To be able to use the program, we need first the global system of coordinates. Easier is to put the origin here, and let's say the x-axis is this one, and the y-axis one. So this is y, and this is x axis. Okay, so let's put, oh sorry, here, capital X, capital Y, and let's put the origin O, or capital O. So the origin is arbitrary, but it's easier to put for this particular example something exactly here. This is x-axis, and this is y-axis. Yeah. The coordinates, or the nodes. So we need node numbers for each point. which define triangle. For that, I will take, let's use blue for node number. So I need node 1, 2, 3, and only 4 nodes here. How will be put the nodes? It's arbitrary. So let's say the node 1 is this one, the node 2 to be this one here, the node 3 to be this one here, and the node 4 to be this one. Also, we need some identification number for elements. Let's say that this is element number 1 and 2. So let's consider element number 1, this one here, and the second is here. So, according to this picture, this first picture here, we can say, okay, the total number of nodes is 4. The total number of elements is 2. And the number of nodes per element is 3, because to define a triangle, we need 3 nodes. Yeah. And let's define an input data file for this one. The coordinates for node 2 is just OR. The coordinates for node 3 is not very difficult to be obtained. Let's write, if you want, here the x, let's write x3 is OR times cosinus from 45 degrees. Yeah. Okay. I need a small circle to be correct there. And due to the symmetry, y it's equal with y3, it's equal with x3. You know that. So everybody know that cosinus from this one is square root from 2 divided by 2. That means a round of 0.7, right? You may also use MATLAB in command line if you want. Let's say if I will calculate from an angle, we must transform in radians. So 45 means pi times the angle divided by 180. And as you can see, if I need also the, you can take this value for the coordinates. And let's keep this file as our file, and you can use for this one save as, this button here, as x1. x1 is my file. And we can remove this one, and you can put something else, is demo1 or something like that, or test1. So general data or data gen. How many nodes? We have 4. How many elements? Only 2. Number of degree of freedom per node. Number of nodes per element, 3. It's okay. So for data node, the coordinates. Let's keep both file open. Yeah, so the node 1 have x and y 0 and 0. Node 2 have x 10 and y 0. Node 3 have let's say 7.07 and 7.07. Node 4 is 0 on X and 10 on Y. And the remaining nodes will be deleted. So data nodes or node data are given here. Data LM. For that, don't forget, you have to read the input, or let's see the problem, even this one here. The node 1 through 2 free. Please keep in mind that this rule must be considered. So don't try to put node 1 to free. We must keep counterclockwise direction, or usually or generally, if you want, is X rotated to Y axis. So for element number 1, I have 1, 2, 3, or you can start with 3, 3, 1, 2, or 2, 3, 1, but not 1, 3, 2, because this is clockwise. It's not good. So here is 1, 2, 3, 1, 2, 3. Element number 2 is 1, 3, 4. Huh, it's perfect. Not necessary to be removed. 1, 3, 4. Let's save this one. Yeah, and you can run it. Let's use command. So the name is, using arrow, you can obtain quicker. X1 was my file. As you can see, I have 4 nodes, 2 elements. It's okay. Number of nodes per element 3. It's okay. Nodal coordinates. Let's say it's okay. If the element data may be okay, I will check the picture. Okay, the picture is okay. You can see node 1, 2, X and Y axis. 1 means this is initial. Yeah. And element number 1, element number 2. Unfortunately, it's not very clear, but let's keep it. Again, enter, and we obtain the cross-section area. It's 70.7. Second moment of area about initial coordinate. This one. Product is no 0 because I have not symmetry here. The first moment of area, this one. Coordinates. So the origin, the centroid is somewhere here. According to this picture, I need 4.02 and 4.02. So from 1 to 2 I have 10, so it's somewhere here. If you want to mark the centroid, okay, with a circle, you can put it somewhere here. Yeah, 4.2. And then more, sorry, click here, more, enter. Second moment of area about centroid, and a new picture with centroid coordinates here, and the principal moment of area, and more a picture with direction of principal, direction 1 and direction 2, and y I1 and A2 and theta are, of course, this angle is multiple of 180 degree. You may remove 180 and you will obtain here 45 degree, this angle. It is this one, but it's the same. Yeah. So these some results here will be put in the A1, A2, and just x1. This is for initial, yeah, and the theta here, just theta 1. And after that, you may start with a different mesh. So a different mesh for the second line will be a more accurate, so more nodes on this curved edge. Let's show you again a new mesh, and after that we will make a new break, and after the break I will finish also the second mesh for a more complex problem, let's say moment 8 or 9. Yeah. And after that you must download the inputs. I will upload all the necessary data on the computer. In the break, don't forget to install the Octave. Yeah, which again I have somewhere here. I don't know where. Here. Yeah. So in the break, take a look at this one and try to put Octave on your computers. If you have MATLAB, but MATLAB is not free. So a break for 10 minutes, okay?
Okay.
Okay. Okay, let's go to let's go back to the applications. So in the break, I put all the inputs in your Moodle platform. Yeah, I suppose that you will be able to download all. What's interesting, unfortunately, I forgot to present you some general information about history of finite elements. Let's discuss after the presentation here. Just a few moments to see something interesting. So there is a list of your group here. You must take your number from this one. Okay. So for example, Alexandru have number 2, Bucur have number 7, and so on. Yeah. Oh, not good to. Was my mistake. Yeah. It's okay. Then you have the problems. Problem 1, 2, 3, and so on, as you know. And as you can see, the geometry here is now so simple. If you want, you can, due to the double symmetry here, you can take, for example, for first application, just this first quarter. If you want to work, better is to work on the complete cross-section. But if not, you can start with a small part, which is a quarter in this case, a quarter maybe here. And as you can see in the right part here, you have a suggestion for the mesh, but it is not complete. It is good, for example, for quadrilaterals with 8 or 9 nodes. Yeah. For triangle, you must split this one also in two, and here is better to take more a rectangle, because when you will use a straight line, you will introduce some errors. Again, 1/4, 1/4. Here is just half, because we have just one axis of symmetry. You split this one in triangle, or you may imagine your personal mesh. Again half, quarter here, quarter, quarter, and here this is complete because it's not very difficult. Yeah, you have also triangle if you want. Quarter again, half here possible, half possible, half possible, quarter, 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 yeah, and here this is also maybe a quarter for this one, and also here a quarter, and so on. Yeah, I suppose that you are no more than 28. We have, and after that, back here must be, this is the file was, this one was downloaded. So for example, because we obtained some results, you must fill for the first mesh. So let's say the student is test 1. Yeah, the problem number, let's say a number, an arbitrary number. Total number of nodes was 4. Total number of elements was 2, and the results, you can take the results from here. Let's start with the last one. Control C, and Control V. Again here, Control C and Control V. And this is X1. So this is according to the first calculus. Control C and Control V. And angle, I told you that our angle is this one, but you can put it this one, or you can remove this one. You can put 25, or if you know 45 is the same, and that's, oh sorry, that's oh, no observation. If you have one, you can put. For the second line here, you can use a new mesh. So I will save also this one in the so let's say mesh 01 for triangle. 3 nodes. Mesh, okay. For example, if you want to improve the mesh, you keep the same input data, and let's use a new one, and again let's draw let's say this is a circle, and I will take just a quarter here. I will remove this one, and the mesh will be more accurate. That means I will take nodes in more points. Okay. So this is, I need here a node. I need here a node. Also here a node. And after that, let's increase the number of nodes. So let's put one at 45 and 2 node between. That means 22.5 and 45 plus 22. Okay, and we can, for example, use this kind of mesh. Let's change the color. So in this case, I will have 4 elements, right? Of course, this is one possibility. Another one is to use many nodes if you want. But in my opinion, it's not necessary to increase very much the number of nodes, because let's, oh, sorry. For example, we can put the node here. Oh, a node here, and so on. It's your business how the mesh will be done. And also one here, and using straight lines. No, black. You will obtain more triangles. And now we must split this one, this one, this one, and this one. And also please keep in mind that using triangles, we have this straight line here. So now the area and also the second moment of area will be obtained better, because now the elements are this one. Of course, here I have no improvement, just here is improved. So this is the reason that this mesh is better than this one, because here I have only 4 elements. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a lot of work. And if you will check that, the results for this one will be exactly the same results as you will obtain using this one. No more difference. Okay. I will omit to build again this one. Just I want to show you something like that. So this is the best, yeah, as the second. Oh, sorry, I need some straight lines here. Sorry, for my dog is okay. I will save this one as mesh number 2. Of course, in the report, it's a good practice to put somewhere here, let's say mesh number 1 for, oh sorry, for triangles with 3 nodes, and you can add here if you want the input data file. Is optional. Please keep in mind that I will correct just this table. You must fill it and upload in Moodle. I will open an assignment there, and the deadline will be next week after the lab. So let's say next week at 2 p.m. To have time to finish if necessary. Okay, you can, if necessary, you can modify a little bit there. This is the reason that I prefer to give you directly the work. And from Octavia, you can take, let's say the last picture is better, because here we can see also the mesh and this axis. You can use, let's say, clear or copy. Here is not copy. If not, you can take, let's say, let's use print screen, and here you can take this one, and this is optional. You can put it here. Oh. And if you want, also the input data may be given here. So if you go into editor, this was my input data file. Why is good this input data file? If I will correct and I will see some mistake, I will take a look here at the input data file and I will show you, okay, here is a mistake, okay, and you will have a feedback for the results. Okay, this is the reason why it's a good practice to put in the reports also input data file. Also, if you want, you can write, I use the code momin and free and so on, point m. It's your option, not necessary, because we know that the subject of this lab is second moment Safari. And okay, after that you may start with this kind of meshes, and I think that the better is to take the last one. So for the last one, please observe that we have quadrilaterals with 9 nodes. Even for this first example, I can take just one element or two. It's our option. And in the last, I will show you more. Okay. Before to continue with the lab, let's go back and take a look at the historical point of view, because I hope that in the future I will not repeat this kind of so this is also a picture from Professor Radesh. So you know the strength of materials. So the strength of materials developed to be began to be developed starting with 1819 with hyperstatic, means structure which are indeterminate. So in Romanian, structuri static nedeterminat. A theorem that energy or energy methods, if you want, was developed by Maxwell later. Castigliano, please remember the theory of Castigliano. After that, the REITs have a very important contribution, and you will see at the finite element course that or mainly the finite element method is a REITs method, or sometimes it's called the Rayleigh-Ritz method. Yeah. This kind of approximation is very important in finite elements. Also, Galerkin have some contribution, and sometimes in different papers you will see that finite element using Galerkin method. The term or the first paper which used a mesh was the paper of the current for torsional study of arbitrary cross section. So please remember that strength of materials you use the torsion for circular cross section, but torsion may be also for rectangular or general shape of the cross section. And Current presented a paper in which he used a mesh to study the torsion of an arbitrary problem. Something similar with what try to do we today. Levy and Garvey have another contribution in aeronautic industry, and then starting with 1955, Argyris and Denke, Turner and Clough introduced the term Clough was the professor, which introduced the term in around of 1966. They worked at Boeing and tried to solve delta wing for a plane. Then another picture here. So the force method at strength of materials was developed starting with after the Second World, and after that displacement method was also developed, and the displacement method was the source of the finite element method, which was started, as I told you, in 1960, around of. Then the finite element. Sorry, yeah.
Vreau să vă spun că până acum nu mi-am mers netul și am fost repede să iau un alt router de la un prieten și acum am rezolvat totul și merg. De asta nu am intrat când a început ora.
Not a problem. No. You may ask the colleagues if you have some problems, or even you may ask me later. So please keep in mind that the finite element method was first implemented on IBM computers, and later, starting with let's say 1980, they was implemented over on mini computers and so on. And more picture with different finite element codes. The first one was Nastran. Nastran was developed at NASA, and it was put in commercial business starting with 1965. Then Aska, Samsef, Stardyne, Asa, Sesam, Sistus, SAP. SAP was free, was developed at Berkeley, and SAP 4 was also implemented in Romania around of 1970. FEM, CAST, FEM, MARC, ANSYS. ANSYS was developed starting with 1970 exactly, and as you and I show you before a little bit about ANSYS, Adina, PAM, and Abacus, and there are a lot of finite element code, but the most important now is Nastran and ANSYS. They are the bigger finite element codes, and that was the history in a few words. You can read it also in the book, so don't hesitate to read here about history. Yeah, so the first course, just some discussion, just to see how the finite element work. Don't nothing about fundamentals. Okay, let's close this one and let's go back to the. I will close the figures. And what's that? Oh, this is the paint. Sorry. Let's start to use the code, the last code. The last is Momin 9. Between is something similar. This is the more complex. So also here you have a directory with some different examples. The examples are also here, and as you know, the main file, so the command file is with the same name as this directory. So let's change the current directory here, but before I will close all the open file and cd and Ctrl V. Now, as you can see, the current directory is this one. Let's start with a test. Let's type mom in 9. And again, we need an input data file. Let's take xmom1, for example. The name must be correct. So this is an example with 25 nodes, 3 elements, and total number of nodes per element, or number of nodes per element is 9, because this is mom in 9. Of course, for each node, x and y coordinates. Enter again to fill all the nodes, and then we have element data here. So for each element, node 1, 2, 3, 4 till node 9 is a list here. Enter again. We obtain the picture for this particular Z cross section. Yeah. The nodes, 1, 2, 3 elements, and as you can see here, the elements are not well connected, but the program works. So the node 8 and node 7 is used to define only this element. This element is defined by 9, so 9 is a common node if you want. You will see later that the correct mesh for real problem is not good if you have some nodes which are not connected to its neighbor elements. Yeah, and again, enter, we obtain for this problem the cross section area, second moment of area, and so on, all the results. And the last picture and the principal moment of area and the angles here. Don't forget, usually the correct theta is this one, minus 180 degrees. I will close the figures and let's start with our problem. So you can open a file, an example, let's say even this one. Oh, sorry. Oh, this is so open is here, sorry. So you can modify this one. This is, let's say, demo 2. And of course, we must start with the same problem and with a new mesh. We keep this one and let's use here a new file. Don't save this one. And let's save as mesh. This may be 2, or let's put directly 9, 3. It's not 3, it's quad. To keep it. So our problem is a quarter of a circle. I will remove here. I will consider straight lines here. Okay, let's move it a little bit here. And the system of axes. Of course, better is to consider the origin as in the previous. This is x and y. This is first step, and it is important. X and capital Y and capital O for origin. So let's move letters. This is the origin, x-axis and y-axis. If you want, you can also use a single element, but it's not good. So I will start first with the mesh. Let's use black. So the mesh will be, let's say, not. I will try a different one. Let's say something like that. I have 1, 2, 3 elements this time. Let's put the circles. Sorry, the nodes, small circle. So I need nodes here because we must define the geometry. I need nodes here. And if you keep this mesh, let's consider here straight lines, and you have quads. Quad 4, the second mesh, which I don't know why this is not active directly. So this one maybe, yeah, but I need this one. This one is better because we have also some curved line. So I will put more nodes here in the middle and also here in the middle, here in the middle, here in the middle, here in the middle, and so on. Hey. And more nodes somewhere inside of each element. Why is necessary to have? Due to the shape function, or if you want, due to the approximation. So for each element I have to put a node somewhere inside here and here. Now we must add, as you can see, each element have nodes on edge, 3 nodes on each edge, and a node in the middle. And you must add numbers for nodes. So I will put more nodes here. Okay, let's suppose that there are enough. So it is not important which node is one and which node is the last one. So I will take one here on this point, node 2, let's say here, node 3, let's say here, node 4, maybe I need a tablet. Sorry. 5 here, 6, 7 here, 8 here, 9 here, 10 here, 11, 12, 13, 14, 15, 16, 17, 18, and 19. Oh. So sometimes we can put a circle or for the last node. So the total number of nodes in this case will be 90. For the elements, we have only 3. Yeah. If I will forget a node, there will be a problem because we must correct the input data file, but it's not so difficult. So 3 elements, element number 1, 2, and 3. Which one is first? Also not important. Let's say this is the element number 1, this is the element number 2, and this is the element number 3. So if I will use, this is 1, this is 2, this is 3. And sometimes, yeah, you can put, if you want, a rectangle here. Yeah. And let's save, and now let's build the input data file. Let's make it smaller here. And now I will correct this input data file. So we have only 19 nodes and 3 elements, and 9 is the number of nodes per element is okay. Then node number 1, it's here. Its coordinates means 0 and 0. Node number 2, we can suppose that this one is a quarter of 10. Or if you use a sketch at scale, you just take a ruler and you can measure this distance. It's not very important. The most important nodes are this one on the boundary, and of course this one, but this one here may be also a little bit not perfect, because if you move this is not a little bit, is not so important. Also the nodes inside of this one may be a little bit moved at the right or left or up or down, and not so important. After you will see the sketch which the program gives us, you can make some correction if necessary. Also, as you can see, this line here may be straight or maybe even a little bit curved if this node is not exactly on this straight line. It's not so important. Also, the middle node, the node inside of this element, usually it may be at cross intersection at intersection of two cross diagonals, or maybe exactly measured. Not very important. So I will put some numbers. If my numbers will be correct, I will see in the picture. So node 2, I will suppose that on x is 2 and on y it's 0. That's exact. Node 3 on x is, let's say, 4 and 0. Node 4, I will suppose it is at 7 and this is 0. And node 5 is 10 on x and 0 on y. Then node number 6. If we keep the symmetry here, I will take again 0 and 2 on y. Node 7, also 0 and, oh no, node 7 is somewhere here. We can take 2 and 2. Node 8 is somewhere here. This one is 4, so maybe 4 and 2. The node number 9, maybe 7 and let's say 3. Node number 10, this is along this circle, so it is important to be exact. And for that, I will suppose that this angle here is 22.5. So for node 10, I will take on x 10 times cosinus from pi. Pi is a constant divided by 180 times 22.5. So this is my, which was supposed to be there. And similarly, for this point, I will take sin from this angle. And this, using these formulas here, I'm sure that the coordinates for this node is exactly on this circle. Okay. For node 11, I will suppose here 4 and 0. For node 12, it's here, I will suppose 2 and 4. Not exactly, but for 13, like we suppose, let's say 4 and 4. And for 14, I will take, let's say 7 is too much, let's say 6 on x and 6 on y. For 15, I will have 0 and 7. I will keep the symmetry because here is 7 and 0. 16, let's say 3 and yeah, 3 is here, and here 7 on y. 17 is over the circle. You know this one from the previous, or we can take this one here, copy, and for coordinates of this node here, I will take 45 here degrees. And for 18, this is clear. This is 0 and 10. And for 19 is also copy. And the angle will be 45 or 90 minus 22.5. Let's keep exactly 75.5. So here 78, sorry, 77.5. The gain. I will remove the unnecessary nodes here. And then we must start with element data, or data elem. And okay, we have 3 nodes, but I will remove this one because probably they are not good. Again, don't forget, the rule is 1, 2, 3, 4, 5, 6, 7, 8, 9. Here, the rule is different for 8. I will keep this rule because if I will change the rule, the picture and the results will be wrong. So the easier is to start from the left in upper direction and so on. So in this case, I will start from this point. So I will have 1, 6, 11, then 2, 7, 12, and then 3, 8, 13. And that's all. The second element is this one. I will start from this line. So it's 3, 8, 13, then 4, 9, 14, and then 5, 10, 17. And the last one is this one. So 11, 18, 12, 16, 19, 30, 40, 17. Okay, let's save and let's check. So the, oh, sorry, I forgot to change the name. So save as, so this is X1 again. Now the name is okay. So let's run again. Oh, while the input data is X1. The program gives us the numbers, maybe okay till now, but it's difficult to check all the coordinates. Let's see how the picture looks. It's not good, right? There is a mistake. So the nodal coordinates may be okay. Let's check. 1, 2. Here is something wrong. This is 11, which is not good, right? You can finish using enter or Control-C to, so my picture was a mistake. So let's go editor and let's check the coordinates for 11. So 11, it's 0 and 4. Let's save and let's run again. Again, I will. Now the picture looks good. Yeah. Of course, this node here may be better is to be exactly in the middle of this area, in the centroid of each area, but it's difficult to put it exactly here. And let's see some results. So the first value is this one, Control C, and let's put it here in the first mesh, this one. Not necessary also. As you can see here, you have E1, this is for centroid. Oh, no, sorry, this is principal. Let's go. The centroid is here. It's, as you can see, it's 4.24. Yeah. Please observe that all these second moment of area are positive. If you will obtain negative, there is a mistake. And for principal value, Control C, let's put it here.
Sorry, Professor.
Yes?
I don't know how to run. I write everything in the editor.
Not a problem. After that, I will have time to show you, yeah, again.
Thank you.
Yeah. Let's finish. And of course, usually to finish this lab, you need more than 4 hours. And the problem was today, because it's the first time when you use this kind of programs, and this is the reason why almost all the time and in the course and also in the lab was spent by me in this. And let's fill also this one, yeah, and the angle, as you can see, is the same as before. So the angle will be 45, and this is the Control B. So this is, let's say, 712, and the first one is smaller. This is 311, and this is 300. Which one is good? In this case, if you want, you can also add or make at conclusion here. We have an analytical solution. And the analytical solution is, we have for area, and we have analytical solution also for second moment of area. Please remember, from strength of materials. Here we have picture. You can add this one, for example, as was before, but I will omit to put here in the report. Yeah, this is your business. Total number of nodes here is 19 and 3. And then you can improve the mesh if you want. Yeah. Check the theoretical results. For this example, it's possible, but for yours particular problem, it's not possible for all. So the area is for circle, as you know, pi times the r square, right? Or in our case is 10. So again, the area is for a complete circle, and for a quarter is this one. So it's 78.5. If you take a look at the program here, you have the area 78.4, 78.5, very close, right? The area. Let's check this one. This is 1964. According to strength of materials, the diameter, of course, is 2 times r is 20, and the ix1 theoretical one is pi times diameter at power 4 divided by 64 divided by 4 because we keep just quarter. And this is 9063, which is close to this one, 9060. So the error is very small, right? So the last one is very close to the analytical solution. The worst are not so good. Why? Because we neglect some parts. So if you want, we approximate the real geometry with one which is with polygonal line there. So using the same rule, you can use the moment 4, 6, and so on. You can fill this one till next week, let's say at 2 p.m. So you must work a little bit home for this first problem. Don't forget, if this lab is perfect, you will obtain 1 point because we have or 10 points. 1 point from 10 because each lab means 5 points. So we have a problem or first application of MOMINERT in 2 labs. So the perfect results for this one means 10 points. In my opinion, this is very important for you. So try to finish and work because the next labs will be similar with this one. But in lab number 3, instead of working with surface elements, we will work with bar elements, truss. But we have more time for that. And then I just show you how the problem can be solved, and you must solve yourself the application because you will have different application and the input data and run the program, it's similar. Just be careful to inputs. This is the main aspect of usually for the lab we have not breaks, but if necessary we can take one, but in my opinion no. So now the first question is, do you have the Octave on your computers?
Yes.
Yes.
Okay. You have these all mom in codes.
Yes.
Yeah, you have them all.
Yes.
Okay, there is not a problem. Then, which one finished to check the code? Let's say which one run a simple existing example, and which one have problems. So I will stop this sharing screen, and there is someone which have problems, and I suggest to so if you want, we can keep also the recording. If not, I will stop later. So now you can share your screen. Which one have problems?
I have some problems.
Try to share your screen. Okay, we can see. So, oh, you try to work in the same time with me. Yeah, it's not a good idea, but usually it's better to check. So this is your input data file. Yeah, it's in momin9, right?
Yes.
Its name is xmom1, right?
Yes.
If you have not mistake, this file must work. Let's save.
The same. Okay.
Yeah.
Previous.
Let's go in the command window.
Okay.
Right. Let's type the name of the program is xmom9.
Oh, okay.
Right.
Oh.
xmom9. Where is the directory? The current directory is this one. It's okay. Let's check that. Do you have this input?
Where?
Let's use the scroll button to no in a current directory.
There.
Yeah. We have xmom9 there. There is. Yeah. So please type xmom.
And I write again here xmom.
Yeah. Enter. Nothing. Why? So a problem may be due to the desktop. Let's put all the files in on the disk D or C. Close this one.
Sir, but
Exit. Use it. You can use exit or just close.
Oh.
Close the Octave. You may also type exit in a command.
So I close that.
Type exit. Exit.
Oh, okay.
Type. Okay. And please, we can see your computer.
Yeah, sorry.
Please share the complete screen. Okay, move this one on C or D.
Okay.
Don't work on the desktop. Do you have D?
I have just C, but
Yeah. Or Octave, yeah.
have one.
But don't use Octave because Octave is the... Okay. So let's...
Go back to Octave, no?
Yeah, you can run. You must change the current directory.
Wait a second to...
Easier, yeah, you can use. It's not on desktop, it's on C. Easier is to use Control C, Control V. But the current directory is on the first line. Please go see in the first. Oh, there. Not okay. No. This is to open. The current directory is on the first line of the window. There is written current directory, not there. Upper.
I don't know where.
Right in the. It's
So
written.
here.
C. No. No. Yeah, you can try to use it. It's your business how you will change the current directory, but the current directory must be in momin9. This is the idea. You can do that using as a line command cd and
Here.
Yeah, there. You must put the correct pass there.
See,
No, it's difficult like that if you know, but yeah. See, right?
yes, that.
Now, momin 9. Okay. And select folder.
Select moment 9, okay? Yes, perfect.
Okay, that's correct. Type again now. Type momin 9. No, you will run not momin 9. Enter. And now it works. Put a name, let's say xmom7. Enter. And this is a test which works. So don't use desktop directly. Maybe some problem this due to the computer. Yeah.
Thank you.
This is the reason why for all of you to use D if you have D, because on C you have also the Windows and.
I understand now. So, and how can I see the graph?
Enter, enter again. Use mouse to click on the if enter don't works, click. No, click on the right.
I see, but I can. I
Enter.
see the figure, but I can show.
Later, enter again.
Right.
Enter. Click and.
Mi-a apărut deja graficul, dar nu pot să-l arăt pentru că am apărut pe doar octav.
Oh, not a problem. It's your business. Okay. So now it works, right?
Yes, perfect.
Okay. Another question. No more questions. So let's, if possible, if you want, let's use the camera to see you a little bit. So I will take my list of presents here and let's, where is my list? I will share my screen again. So later you will have homework. So the homework looks something like that, and the problems is 4 problems for homework. Yeah, we have a lot, but starting with week number 8, because the homework is part of the final exam. I suppose that I have, this is my last list. So if possible, let's make the first presents directly here. No, this is PDF. Let's open this one. So Akiniazov is here, or it's absent. It is absent. He is absent. He or she?
He. We don't know
The girl.
if he's
Okay.
here.
She is absent today. Andrea Alexandru. Sorry?
He's a boy.
No. Andrei is here, I suppose.
Andrei is here,
right?
yes. Number 2 is here.
The boss. May we have a may we use a little bit, if possible, if not necessary, the camera to see you.
Wait a minute.
Just a minute. Okay. Hello. Oh, no, this is you, Victor. It's not you, Alexandru. Where is Alexandru?
I'm putting my camera right now.
Okay. Okay, it's a good idea to use camera, but not all the, not necessary. Hello.
Can you
Yeah.
see me? Hello?
Yeah. Okay. That's good. So you are present. That's working. Then let's see. Oh, let's close this one. Let's keep just this one. So he is present here. Okay, I can't download the list of presents, but this is the classical, this is the old method. So Mustafa Al-Ojaidi is here.
Yes, sir.
Can we see you a little bit, if possible, just if it is possible. If not, you can see that not possible and say not a problem. Okay, I will close the recording because it's no more so important.